in this talk, I will introduce our recent work on the Julia package ZXCalculus.jl. First, let me introduce myself. I'm Chen Zhao, a PhD student from Chinese Academy of Science. This project is for Google Summer of Code this year, and this project is mentored by Roger Luo and Jingguo Liu. Also, this is an open source project, and you can find it on GitHub. And here is the link for this project. Also, this notebook is also available on GitHub, and this is the link. Okay, let's begin the. Firstly, I will introduce the ecosystem of Yao, and then I will show how to use ZXCalculus from the high level as a circuit optimizer and to the low level. Finally, I will talk about why we developed ZXCalculus. Yao is a Julia framework for developing quantum algorithms, and it's named after the Chinese character of the unitary. Yao, this is the Chinese character. And Yao framework is built around a hardware-free intermediate representation, the quantum block intermediate representation. We call them QBIR. And you can express your quantum algorithm as QBIR in Yao. Also, you can apply the QBIR on different quantum registers depending on different devices. Moreover, you can use the automatical differentiation tool in Yao to differentiate your quantum circuit. Also, symbolic computation is supported. And you can convert the QBIR to symbolic matrices. All of this built up with the Julia programming language, so you can connect the quantum algorithm defined in Yao with other Julia ecosystem easily. This includes the differential equation and the flux and zygote for machine learning and automatic differentiation, and the Julia statistic ecosystem, and Julia optimization ecosystem, and so on. Thanks to Julia ecosystems, Yao's framework is very generic and efficient. For example, in Yao, we used only 300 lines of code to support the QDA GPU. And here are benchmarks for Yao and other quantum computing softwares. And in this picture, you can see Yao reaches the state-of-art performance. And recently, we are working on Yaoland, a new quantum domain-specific language. It is for compiling hybrid quantum classical programs in Julia, and it extends the Julia grammar such that you can define hybrid quantum classical programs in Julia easily. Also, Yaoland will generate generate instructions for different devices, depend on the hardware backend. And here is a GIF for Yaoland. In this GIF, we define a generic quantum Fourier transformation of n qubits in Yaoland. And we generated a 4-qubit QFT circuit and apply it on a 4-qubit random state. And ZXCalculus is integrated with Yaoland. And next, I will briefly introduce how to use ZXCalculus as a circuit optimizer in Yaoland. To define a quantum circuit in Yaoland, one can use the macro at device. In any function which is decorated by the macro at device, you can use the command J arrow U, this means apply the gate U on the J's qubit. And you can use the add control macro, add control J K arrow U. This means apply the control U gate on the J's and the K's qubit, where the J's qubit is the controlling qubit and the K's qubit is the target qubit. Here is an example that defines a 4-qubit circuit with 20 gates. And this with the at-device macro, and we define a demo circuit. And for example, in this line, this means apply a Hadamard gate on the 4th qubit. And this line means apply the CZ gate on the 1st and the 2nd qubit. And this defines a quantum circuit. So how we call the optimizer in Yao-Lan? We can simply add an argument optimizer equals OPTS to call the backend optimizer. Currently, there are 2 optimizers supported. The first one is the ZX teleport for the phase teleportation algorithm, which developed in this article. And the ZX Clifford for the Clifford simplification based on the circuit extraction algorithm, which is developed in this paper. In this example, we define a quantum circuit. The gates are just same as the last circuit, but we call the optimizer the ZX teleport, and this will tell the compiler in Yao-Lan to call the circuit simplification algorithm to optimize this circuit. So let's see the result. By using the Yao-Lan function gate count, we can see how many and what kind of gates we have in a circuit. For example, in the original circuit, which is the demo circuit, there is 20 gates, and there are 2 T gates and 2 T dagger. And in the simplified circuit, there are only 14 gates and only 1 T gate and 1 T dagger. So the circuit is actually simplified. And also with Yao-Lan, Yao-Lan can compile quantum programs to instructions that can be run on different devices. For example, we can use the quantum simulator in Yao as the backend. In this example, we use the Yao array register and define registers and apply the circuits we defined on them. And we just using the Yao array register, and we define 2 random states. And because we are using the simulator, we can copy this state. And we define the circuit and the simplified circuit. And we apply the original circuit on rich and the simplified circuit on rich simplified. And by using the fidelity function in Yao array register, we can check whether these 2 states are equivalent. And you can see the fidelity of these 2 states is approximate to 1. This means these 2 circuits are equivalent. And also, we can load QASM code to ZXCalculus to show how to use the QASM, how to load QASM code. We first see the landscape of the Yao-Lan. In Yao-Lan, quantum programs are represented as a static single assignment form intermediate representation. We call them Yao.ir. And all hybrid program will compile to Yao.ir. Then we use the code optimizer to optimize it. The optimized Yao.ir will be compiled to quantum instructions depend on the device. And to load QASM code, we first load QASM code to Yao.irs, then we convert the Yao.ir to ZXDiagrams. This is how the loader in ZXCalculus be implemented. And here are APIs for loading ZXDiagrams. For example, we load QASM code from a file. Then we simply use the constructor to construct the ZXDiagram directly. We use the ZXDiagram constructor on the source code and with the identifier of the QASM. Then it will generate a ZXDiagram corresponding to this circuit. Then we can call the phase teleportation or the Clifford simplification to simplify this circuit. For example, we use the phase teleportation on the ZXDiagram we loaded from the QASM code, and we check out the change of t count by using the function t count on the ZXDiagram. We can see the original circuit, there are 448 t counts, and in the simplified circuit, there are only 264 t counts. By now, we have shown how to use ZXCalculus as a circuit simplification engine, and let's open the blackboard to see how it works. And I will talk more details about ZXCalculus. First, I want to talk about the data structure. In ZXCalculus, general ZX diagrams are stored in the data structure ZXDiagram, and the graphical backend of ZXDiagram is the multigraph. And we implemented Julia multigraph library, the multigraph.jl, based on the Julia graph library multigraphs. And this multigraph library also open source. And we can construct a ZXDiagram from multigraph directly. In this example, we define a multigraph with 6 vertices, and we add some edges into this multigraph. Then we define the face for each vertices and the spider type for each vertices. Then we can use the constructor ZXDiagram on the multigraph and the face and the spider type. And here is the multigraph. Here is the ZXDiagram we get. You can see the result. But it will be very complicated when constructing large-scale ZXDiagrams. So it is more recommended to construct ZXDiagram from quantum circuits. In ZXCalculus, the Q circuit is the data structure for representing quantum circuits. And you can use the Q circuit N to generate an empty n-qubit circuit. And you can use the pushGate function to push gate into this circuit. And in this example, we pushed 5 gates to a 2-qubit circuit. And here is the circuit we get. And then we can construct the ZX diagram from quantum circuit directly by using the constructor. And in this example, we generate a random circuit. We generate a 4-qubit circuit with 40 gates and convert it to a ZX diagram. And this is the ZX diagram we get. And after constructing ZX diagrams, we can rewrite ZX diagram with the ZXCalculus rules. And in ZXCalculus, we can use the match function to match all the available vertices in ZX diagram for a specific rule. Also, we can use the rewrite function to rewrite ZX diagram on the matched vertices. Or more simply, we can just use the replace function to match and rewrite. The replace function is the combination of match and rewrite. Or you can use.
Can you hear me?
Yes.
Yes. Is the match function, is that finding a bunch of non-overlapping matches?
Yes, but the vertices maybe has overlap.
The match vertices may overlap. Okay.
And when we call the rewrite function, it will check whether this matched vertices are available.
Okay, so does it apply only one of the matches, or does it apply as many as it can?
As many as you can.
Okay, thanks.
And the simplification function, the simplify function will do the replace recursively. And for example, we have 7 rules for ZX diagram, and these rules are the basic ZX calculus rules. And for example, we applied the H rule to simplify the ZX diagram we generated, and then I1 rule and I2 rule. And you can see in this simplified ZX diagram, there are no X spiders. And in ZX calculus, we defined another kind of ZX diagram called graph-like ZX diagram. And it is first introduced in the graph theoretic simplification of a quantum circuit. And the graph-like ZX diagram is very useful in many simplification algorithms. We store this data structure as the ZXGraph, and we can simply convert a ZX diagram to ZXGraph with the constructor ZXGraph and on a ZX diagram. For example, the ZXDiagram is the ZX diagram we generated, and we call the constructor ZXGraph. And we get a ZXGraph. The constructor will automatically call the simplify routine in the constructor. Then we can also apply rules on ZX graphs And these 7 rules are defined in these 2 papers. And in this example, we apply the LC rule and P1 and PAV rule on this ZX graph. And this is the simplified ZX graph. And then we can use the circuit extraction algorithm to extract a new circuit. Just call the circuit extraction on a ZX graph. And here is the extracted circuit. And we can convert the ZXDiagram back to Q circuit. And you can see there are only 34 gates in this simplified circuit. And also you can combine these two algorithms together. And also the visualization tools are available in the Julia package Yao.jl. And if you want to draw a diagram for a ZXDiagram or a ZXGraph, you can just using the Yao.plot package, and after defining your ZXDiagram or ZXGraph, you just use the plot function to plot it. And for this example, we generate a 4-qubit circuit with 10 gates and convert it to ZXDiagram and plot it. And you can see the result. Each time the circuit is different. Now let me explain why we developed the ZXCalculus. The phase teleportation and the circuit extraction algorithm are implemented in the Python package pyzx. And pyzx is a full-feature library for ZXCalculus. And it provides many amazing features of visualization, and it supports different forms of quantum circuit, including QASM, Kuiper, and quantomatic. And why we developed ZXCalculus.jl, the first reason that we need a lightweight circuit simplification engine for the Yao-lan, the compiler. And if we use the pyzx as the backend, it will be more complicated to maintain 2 languages in one package. Also, the Julia is faster than Python, and we do benchmark test on for the phase teleportation algorithm on 40 circuits with ZXCalculus and pyzx. And the test results show the ZXCalculus has 6 times to 50 times speed up on different circuits. And here is a picture for the result. In this picture, the runtime of the ZXCalculus of to be 1. And that's all. Thank you.
Let's thank the speaker. Any questions?
Yeah, I have a question. I guess a simple one is the code all online now?
Yes. The codes are available on GitHub, and here is the link.
Ah. Great, thanks.
What paper did you said you use the identities from? I didn't get enough time to look at it.
Sorry, I didn't hear it clearly.
Like, which paper did you get which fragment of the ZX calculus are you working with? You showed it on the screen, but I couldn't see because my internet cut out.
Which paper? You mean
for the rules? Yeah.
These rules are from the phase teleportation, the reducing T count with ZXCalculus and graph theoretic simplification. These two papers.
Thank you. Neil has his hand up, I think.
Hi, yes, thanks. For those of us who are not very familiar with Julia, you commented on the performance difference between Julia and Python. I'm aware of Julia as something in which you can do easily formally verified work. Could you comment on the role of Julia and why it has much better performance than Python, and why as a language it might be suitable for quantum technologies in this way?
Maybe this question is more suitable for Roger Luo, and I don't know whether he is online. And for me, the developing Julia packages is more efficient, and you can get pretty good performance without many optimization. And the Julia language, there are many there are many benchmarks for example that Julia can approach the performance like C.
Okay, that's good to know about. Thank you.
I have a question about this benchmark plot, actually. So it looks curious that the ZXCalculus.jl times all seem to be exactly the same. Is that true, or are they just all very close and we can't tell the difference?
The runtime of the ZXCalculus are scaled to be 1.
Oh, I see. Okay, so the blue bar is the number of times the original of the ZXCalculus one.
Yes.
Not something like
the blue bar is the runtime for physics, and scale to be the runtime of ZXCalculus are scaled to be 1, and
okay, yeah.
the blue bar is the runtime for physics on the same scale.
Okay, that's clear.
Looking at this plot, it seems like for most of the benchmark circuits, the sort of PyzX is about 10 times slower, but then there's a few outliers where PyzX is doing much worse. Do you have any idea why that is? Do those circuits have specific properties that just make either PyzX particularly bad or ZXCalculus.jl particularly good?
Actually, there are 2 examples for ZXCalculus that cannot reach the T count as physics. The T count in this 2Z example for ZX calculus is a little bit higher, but we are still investigate the reason. But for runtime, ZX calculus is always faster.
Hey, maybe this will help. Just from a quick eyeball of this plot, Miriam, I think the ones where the bars are really high are really, really big circuits.
Yes, yes.
So this is a set of benchmarks of kind of all different circuit sizes, and those seem to be the really big ones.
The biggest one, I think, is the HWB 10, and it is for bigger circuits, the ZX calculus may faster.
That kind of suggests that there's some asymptotic difference, not just constant overhead. That it's faster.
So I see that Harney asked in the chat, what are the two circuits where you get a different T count from pyzx? You know?
It is the cycle 17.3 and the mode adder 1048576.
Okay.
Did you check that both pyzx and ZXCalculus.jl give the correct results, like that they don't make any mistakes in terms of translating the circuits?
Yes, we checked by using the Yao and we checked the equivalent of the simplified circuit and the original circuit.
And they're the same for both ZXCalculus and for pyzx? Or did you just check for your implementation?
For large circuit, we can't check the equivalent because the simulator cannot run such a site. But for some small circuit, I checked the equivalent, but for physics and ZX calculus, I just checked the T count.
Right.
Hi, just a note that if you import those very big circuits into pyzx, you can use the verify equality function on the circuits to check equality for very large circuits. Because that just uses this ZXCalculus to reduce it to the identity. So that there could be an extra check that those big circuits are indeed still the identity. Although yes, I'm not sure if it would work on those really, really large circuits.
It is a good method, but we didn't try it.
Yeah, I'm just saying because like I know from my side implementing this phase teleportation routine, like it had some very subtle bugs on large circuits that only appeared on large circuits. So that's why I'm, yeah, like you need to be really careful with this implementation because it's very tricky, like at least in my experience.
Yes.
This is just a comment that, if I recall correctly, there was a talk at ACT this year, Applied Category Theory, where someone also used Julia to kind of work with monoidal categories or something, symmetric monoidal categories, in a way that the quantum group had been doing it with Python before, and apparently it was faster as well. So this is the only person to have the idea to use Julia to like speed things up. So this is kind of exciting, I guess.
There is a Julia package catlab for the category, and maybe we can connect ZXCalculus with the catlab as a example of the category. Maybe.
That'd be cool. Are there any more questions for the speaker? In that case, let's thank Chen again.
Thank you.